Okay, good morning or good afternoon, and in this lecture video, we will be covering our energy and our energy diagrams. So let's start with energy. So energy is defined as the capacity to do work. In chemistry, we have two general types of chemistry, which is our potential energy and our kinetic energy. When we say potential energy, this is energy that is not moving, or it is stored energy. While for kinetic energy, it is the energy of movement or the energy of motion. This is the energy that our atoms exert when they move from one place to another. So here's an illustration between potential energy and the kinetic energy. This is the classic image for demonstrating potential energy. When we say potential energy, it has the capacity to move, while kinetic energy is the energy of movement. Potential energy can be converted to kinetic energy when the item starts to move. And to regulate our energy, we have the first rule of our thermodynamics. Thermodynamics states that energy cannot be created nor destroyed. It can be converted from one form to another, like potential to kinetic and kinetic to potential, but it is never lost, even if there is an inefficiency in the conversion of forms of energy. Most of the times, you would account for all the energy lost or energy gained via heat. So sometimes energy transforms into heat energy. So the total energy in the universe does not change based on the first rule of thermodynamics. The energy stored in chemical bonds, both ionic and covalent, is a form of potential energy. So in chemical reactions, the potential energy may be released and be converted to heat and the kinetic energy of the moving particles of the product. Reactions that form products having lower potential energy than the reactants are favored. High energy substances tend to form lower energy substances, since lower energy substances tend to be more stable and higher energy substances tend to be less stable. So to be familiar with the units of energy, although we don't need to compute energy for a while, when we say calorie, it's the amount of energy required to heat up 1 gram of water by 1 degree Celsius. And another common unit we use is joules. So 1 calorie equals 4.184 joules. So in terms of energy changes and reactions, when molecules come together and react, bonds are broken in the reactants and new bonds are formed in the products. So most of the time when we are performing chemical reactions, our bonds break and bonds form. So breaking a bond requires energy. So in this case, in our illustration, chlorine molecule needs 58 calories to break the bond between the two chlorine molecules. So when breaking bonds, you need to add energy. However, when you are forming bonds, you need to remove energy. So when two substances form bonds, the product tend to be lesser in energy, hence energy must be released. So in contrast, when the chlorine-chlorine bond is formed, 58 kilocalories of energy is released. The amount of energy needed to break the bond is the same amount that is released when the bond is formed. So when bonds are broken, it always requires an input of energy, and bond formation always releases energy. The energy absorbed or released in the reaction is called the heat of reaction, or enthalpy change, symbolized by our our delta H. The heat of the reaction is given as a positive or a negative sign depending on when energy is absorbed or energy is released. So when energy is absorbed, the reaction is said to be endothermic. It absorbs heat, meaning you add heat, so the change of heat is positive. You add more heat. When the energy is released, the reaction is said to be exothermic. You give off heat, hence the difference of energy is negative since you released or lost heat. So when we say bond dissociation energy, the heat of reaction for breaking a covalent bond by equally dividing the electrons between two atoms in the bond is called your bond dissociation energy. Because bond breaking always requires energy, bond dissociation energies are always positive numbers. And breaking a covalent bond into atoms that compose it is always endothermic. So when breaking substances, it's usually, most of the time, endothermic. And because bond formation always releases energy, forming a bond is always exothermic and the enthalpy change is negative. So take for example, this is the formation of hydrogen molecule. When you form hydrogen molecules from two atoms of hydrogen, you release heat. However, if you break a hydrogen-hydrogen bond into form two atoms of hydrogen, you need to add heat. Bond dissociation energies tell us about bond strength. The stronger the bond, the higher its bond dissociation energy. So in terms of endothermic and exothermic reactions, most reactions involve breaking and forming more than one bond. So in these instances, the heat of reaction measures the difference between the energy to break bonds and the energy released from bonds. So mathematically, you subtract products from reactants. You subtract the product's heat from the reactant's heat. So the delta H total indicates the relative strength of the bonds broken and formed in the reaction. When enthalpy is negative, the reaction is endothermic because more energy was released in forming bonds than breaking bonds. So the bonds formed in the products are stronger than the bonds broken in the reactants, hence the reaction is exothermic. An example of which is your combustion. So combustion occurs when your fuel, in the case of this reaction, methane reacts with oxygen to form carbon dioxide, water, and release of heat. This is what happens when you burn fuel. You change the hydrocarbon into carbon dioxide and water, and you have a large byproduct of heat. So in this case, the enthalpy is negative, meaning the reaction is exothermic. The bonds formed are stronger than the bonds broken, and since more energy is released in forming the bonds in carbon dioxide and water than it is absorbed in breaking the bonds between methane and oxygen. So since energy is released, products are lower in energy than the reactants. These products are much more stable than these reactants. Next, when enthalpy is positive, this is the opposite, more energy is needed to break the bonds than it is released in forming the bonds. The bonds broken in the reactants are stronger than the bonds formed in the product, and the reaction is endothermic. A good example of this is your photosynthesis. So in photosynthesis, you need to add heat to convert your carbon dioxide and water to form your sugar and oxygen as a byproduct. So since you need to add heat, it is endothermic. So in this reaction, energy is absorbed, enthalpy is positive, and reaction is endothermic. The bonds broken are stronger than the bonds formed because more energy is needed to break the bonds in carbon dioxide and water than it is released in forming the bonds in glucose and oxygen. Because energy is absorbed, the products are higher in energy than the reactants. So here is the summary of our endothermic and exothermic reactions. So next is what is needed for reactions to occur. So there is a kinetic molecular theory for reaction kinetics. But to simplify, they must collide in the right orientation, meaning there is a right position for reactions to occur, and the kinetic energy must be enough to break bonds. In any given sample, molecules possess a wide range of kinetic energies, and this kinetic energy is mostly tied to temperature or heat. The higher the temperature of substance, the higher it is in energy, and sometimes that is the reason why some reactions do not occur when you are not heating the chemical reaction. So the energy changes in reaction are often illustrated in an energy diagram, which plots the energy on the vertical axis or the y-axis, and the progress of reaction, the reaction coordinate, on the x-axis or the horizontal axis. The reactants are written on the left side and the products on the right side, showing that products are turned into reactants, and a smooth curve that illustrates them how energy changes with the time connects them. So here is an illustration of an energy diagram. So have your reactants on the left side and your products on the right side. Please take a look, and this would be hopefully this would be familiar to you when you take your exam. So this is the energy diagram. Energy is on the x-axis or the y-axis, while reaction coordinate is on the x-axis. As the line goes up, the higher in energy it also goes up. And the lower it goes, the lower the energy goes. Reaction coordinate takes into consideration how far the reaction is going. Eventually, reactants would turn into products. Okay. So when reactants A, B, and C approach each other, their electron clouds feel some repulsion, causing an increase in energy until a maximum value is reached. This is it. This maximum energy state is called your transition state. So at this state, your reactants could turn into products or could turn back into reactants. So in the transition state, the bond between A and B is partially broken, and the bond between B and C is partially formed. At the transition state, the bond between A and B can reform to regenerate reactants, or the bond between C and T can regenerate to form products. So as the bonds form between B and C, which is the products, the energy decreases until some stable energy minimum is reached. The products are drawn lower in energy than the reactants to reflect the initial assumptions about their relative energies. So in this case, the assumption is you have a higher energy reactant and a lower energy product. Hence, heat would be released. So the difference in the energy between the reactants and the transition state is called your activation energy, or your EA. This activation energy is the minimum amount of energy required for the reaction to occur. It represents the amount of energy that the reactants must possess for the reactions to take place. If your reaction doesn't have enough energy, the reaction won't proceed. And most of the time, this is related to heat. The energy of activation is often called the energy barrier that must be crossed. The height of the energy barrier, or the magnitude of the energy of activation, determines the reaction rate, how fast the reaction occurs. So please take note of this. As energy of activation increases, meaning if you have a steeper curve, the slower the reaction is. And if you have a lower activation energy, meaning you have a low EA, the faster the reaction would take place. This would have an effect later in our catalyst. So just take note: high EA, low reaction rate; low EA, fast reaction rate. So here is an energy diagram for an endothermic reaction. The first one was an exothermic reaction, since the products were lower in energy compared to the reactants. This is the opposite. Your reactants are lower than the products, meaning once your reactants reach the transition state and end with the product, your products are higher than the reactants, meaning you added heat to form the products. And this is an endothermic reaction. Okay? So EA is the energy difference between the reactants and transition state. Delta H, or your enthalpy, is the difference in energy between the reactants and products. Because the products are higher in energy than the reactants, enthalpy is positive and the reaction is endothermic. So interpretations of your activation energy. When the energy of activation is high, only few molecules have enough energy for the reaction to proceed. When the energy of activation is low, many molecules have enough energy to cross the energy barrier, hence the reaction is faster. The difference in energy between reactants and products is the enthalpy, which is also labeled on the energy diagram. When the products are lower in energy than the reactants, as in the case, the bonds in the product are stronger than the bonds in the reactants. Hence, delta H is negative and reaction is exothermic. Finally, last note on activation energy. An energy diagram is a visual tool that helps us illustrate both the rate of reaction by the height of the energy barrier and the energy difference. Keep in mind that these two quantities are independent. A large EA does not tell us anything about the relative energies of the reactants and products, and it doesn't tell us anything about the heat of reactions. Finally, we have some catalysts. When we say catalysts, these are substances added to the chemical reaction, most of the time placed above the reaction directionality arrow, and this helps the reaction move forward. A catalyst is a substance that speeds up the rate of the reaction. It is recovered unchanged in the reaction. It does not participate in the reaction, nor it is used up, nor does it appear in the product. It only helps speed up the reaction, but in chemical and stoichiometric terms, it does not participate. They accelerate a reaction by lowering the energy of activation. They have no effect on the energies of the reactants and products, and the addition of catalyst lowers EA but does not affect delta H. So here's the effect of a catalyst on a reaction. Here you go. So here, the blue one is when it is uncatalyzed. You require a higher energy barrier for the reaction to proceed. However, if you catalyze the reaction, you would end up with a lower activation energy, giving you a faster reaction. Since a catalyst lowers the energy of activation, increasing the rate of catalyzed reactions. The energy of the reactants and products is the same in both the catalyzed and uncatalyzed reactions. Okay, that concludes our lecture for today. Hopefully you learned something. Thank you for listening and have a nice day.